you'll see a graph Java file. That Java file implements this API. So we have a couple of ways of building graphs. You'll see this top one here is a constructor that builds an empty graph with V number of vertices. So capital V will stand for the number of vertices in a graph, and capital E will stand for the number of edges, as you'll see in the implementation itself. So, but to build a graph, you can pass an integer, V, and the graph API. Let me see if I can bring up, here's the graph API. So we can bring up the structure, I guess. So here's graph. This is the constructor that we had on the slide here. So here's the slide. Here's the slide. And here's the implementation. So on the slide, you had the constructor. And this is how the constructor builds the graph, an empty graph. So you have a bunch of private instance variables in the graph API. V is the number of vertices, E is the number of edges. So when you build this graph, when you say graph 5 vertices, it sets V to 5, number of edges is still 0, and then it builds something here. Okay. For each vertex, you will notice that you have an array list, a list of something. Okay, so you have ADJ here, it stands for the adjacency list. Okay. It's an array list of integers, and its length is B. So I have as many adjacency lists as I have vertices in this graph. Okay, so let's take a look here. We also want to make, we have a couple of extra methods. Oh, okay, so we have another graph in here. This is a constructor also. This allows you to read a file. Here it is. This has all sort of file reading capability here built in. So it reads a file. So you don't have to normally have to worry about it, but you should be able to read this code and see what it does. The way graphs are represented for us. So let's give an example of a graph. Here's a graph called TinyG. It's a small graph. It's one of those graphs that you see on the slides. It has 13 vertices and 13 edges. These are the connections, 0 to 5. Apparently there isn't. So have 13 vertices. The vertices are numbered 0 through 12. Okay. And then you have an edge from 0 to 5, from 4 to 3, and so on and so forth. So let's take a look at the, let's take a look at this graph. So here's a graph on 13 vertices. You see that the vertices are numbered 0 through 12. In fact, this is the graph. I think this is exactly the graph that's there. Okay, so 0, 5. You see there's an edge, 0, 5, 0, 1, 0, 2, 0, 6. Okay, 0, 5, 0, 1, 0, 2, 0, 6. All those edges are present. So you represent those edges here in pairs of integers. The graph constructor reads this graph. So you say all you have to do in your homework assignment is just simply use this in. We did this, so this is done in just one line. So you create this new in object just to read the file. You still have your in class here. This is the same reader as before. You should be familiar with this one. So inside graph, you say just in, read the file name, and you construct the graph immediately. And this version of the graph also has the print, the toString method here somewhere. There it is. That simply allows you to print the graph. So if you just run this, you'll see that the graph is printed here. So here's a graph. It tells me it has 13 vertices, 13 edges, and it gives me the adjacency lists. So these are, you have these 13 adjacency lists are that ADJ, this ADJ. Okay, this ADJ here declared at the very top, this ADJ are the adjacency lists. For each vertex, I have a list of vertices that are adjacent to it. This will be our graph representation. We read this text file that lists the edges, and from that list of edges, we construct the adjacency list representation of a graph. And here you have it. So 0, this first line, for example, tells me that 0's adjacency list is 5, 1, 2, 6. What does that mean? It simply means that the vertex whose name is 0 is connected to 5, 1, 2, 6. Where is it? There's 0, 5, 1, 2, 6. That's who 2, 0 is connected to. Same thing with any other vertex in this graph. So you take, for example, 7. 7 is only connected to 8. Let's take a look at what the output tells me. I look at 7's adjacency list. There's only one guy at 7's adjacency list. In 7's adjacency list, there's only one guy called 8 is there. 8's adjacency list, there's only one guy called 7 is there. This is called an adjacency list representation of a graph. There are other representations of graphs. Adjacency matrix representation, for example, incidence matrix representation, so on and so forth. But this is the most efficient one for our purposes. So we'll stick with this one without bothering with the other representations, although we do have to mention the adjacency matrix representation and discuss the advantages, disadvantages relative to each other of these two different representations of graphs. So let's move on a little bit. Let's end this check-in. Everybody has checked in, pretty sure. Okay, so this is our graph API. So you get this idea. You have all these methods inside. These guys, the last two methods, simply return to the user the number of vertices and the number of edges. These are convenience methods. The most important ones are the constructors that build the graphs using these methods here. You can add an edge. Once you've built the graph, you can add an edge to it, and you can iterate through the adjacency list. We'll find that useful in the algorithms to come that we'll discuss today. So here's a typical graph processing code that computes the degree of a vertex. So suppose you want to know what's the degree of a vertex, please remind me.
The number of edges.
Yeah, the number of edges incident to it. That is the number of its neighbors, the number of other vertices in the graph that it is connected to. Okay, so you simply look at the adjacency list. So how do you determine the degree of a graph? Well, what's the degree of this vertex 0? Well, it's on its adjacency list, you have 4 guys. Yes, 4 guys are connected to it, 4 neighbors. 4 neighbors. Therefore, you just go through the list and the adjacency list and increment the degree here and then return this degree. Degree is the number of the elements on the adjacency list of this vertex V here. Pretty simple. Okay, so here's, what does this one do? Let's print each edge twice. I just want to copy this, but it's not happening. So you get the idea. You can print each edge twice. Actually, why not do this? Although we don't want to spend too much time on this. Kind of here, kind of there. Okay, so here's my graph. Here's my graph. Okay, so why don't we type in this code? Okay. I don't have my keyboard here, but this keyboard here will do. So you take each vertex here, start from vertex 0, and you go up to what? The graphs. How many vertices does the graph have? So here's my graph G. Okay, here's the number of vertices that the graph has. So iterate through the vertices. You know that you're able to iterate through the vertices. And then look at every vertex, denoted here by W, that is inside, okay, for every vertex that is inside the adjacency list of V, right? Does it make sense what this code is doing? And then you simply print out this vertex V, which is going to be an integer. So I'll allow Java to just simply print this. And then I'm going to print this little dash here to tell me that V is connected to this vertex W. So this is essentially, I'm copying this code. And by the way, this prints, so prints each, why does it print, so let's see what it prints. Okay, why does it print each edge twice? Just to make sure that we're on the same page. So I've printed all the edges in this graph. If you look at the number of entries here, you'll see that I have 26 lines. Why do I have twice 13 lines? This graph here, we're talking about this particular graph here, has 13 edges. Why did I print each edge twice?
Because you're going through each, so like for the first iteration of that outer for loop, you're going through each vertex and printing what it's connected to. And then that same edge will be repeated when you're going through
Yes.
the next vertex that it's connected to.
That's exactly right. Does everyone agree? Okay, so that's exactly what's happening. Okay, so let's see. So here's a typical graph processing code. You sometimes want to compute the degree of V. We just did that. Okay, so this is what we just ran. You want to compute the maximum degree of a graph. So you're given this giant graph, and you want to know which special vertex is it that's connected to the most number of other vertices. You might want to compute the average degree of the graph of a vertex in a graph, right? So if you think about it, the average degree is going to be twice the number of edges divided by the number of vertices in the graph, right? This follows from something called handshake lemma. We're not going to discuss it in detail, but you can think about it. So if you add up all the degrees of the graph, so if you add up how many elements you have on all the adjacency lists, you will see that for each vertex, for each edge in the graph will be accounted exactly twice, right? So if you go through, for example, suppose U and W are connected. U and W are vertices in the graph, in graph G. W appears once in U's adjacency list, and U appears once in W's adjacency list, right? So this edge UW, when you look at all the adjacency lists, that edge UW has been accounted twice once you're done looking through all the adjacency lists of the graph. So twice the number of edges is going to be the sum of all degrees. Then what's the average degree then? Is, well, twice the number of edges divided by the number of vertices that I have. Okay, so you have a bunch of examples here, the typical ways of using graphs. So there is another way of representing graphs. This is called an adjacency matrix representation. So you list the vertices. So suppose you have n vertices, in this case 13. So it's going to be a 13 by 13 matrix. And it's going to be, for a simple graph like this, it's going to have entries, either zeros or ones. So in the ijth position, you have an entry of 1 if and only if I and j are connected. Okay. So for example, in 5, 4 entry here, this is 5, 4 entry, the 5th row and 4th column. This 1 here tells me that 5 and 4 are connected in this graph. Notice that there is no, for example, why is there a 0 in 0, 4 entry? Where's 0, 4? 0, 4, here it is. 0, 4 entry, that's because there's no edge between 0 and 4. So this is 0. And notice to store a graph that has billions of vertices, you need billion squared cells in your memory to store these zeros and ones. And that can become pretty expensive. Okay, so on the other hand, I will be asking you in a second, how about the adjacency list representation that we prefer? Well, how much memory does that take? Well, can I ask you that? And how much memory would that take in terms of the number of vertices you want to think about, or the number of edges? What's the most amount of memory that can take?
If every node was connected to every other node, then it would also be a billion times a billion, wouldn't it?
Yes, the half of it, close to it. Yes, if you have very, very, very many edges, if it's what's called a complete graph, then you have billion half. Okay, so well, one edge. Okay, so actually it's going to be billion because if each edge is represented twice, and the way we have it, we actually do have each edge represented twice. So that's going to be close to billion, right? Squared. In fact, if you have self loops, like if you allow 0 connected to itself, like self loops like this, which we're not considering, then will be exactly billion squared. However, in real life applications, what happens is that the average degree of although you may have way too many vertices in a graph, for example, in a Facebook graph, you have billions and billions of vertices, like, right? Okay, but the average degree of a vertex is pretty small. You know, so most people have a few friends. Okay, there are people that have hundreds of friends. Some people have like a couple of friends. So average degree is no more than a few dozen, right? Maybe. So you don't want to waste that much space, right? So it's much easier to have a billion entries, like in the adjacency list representation, a billion entries for each vertex. So each vertex needs an adjacency list, but each adjacency list has, an average like 12 entries. So that's 12 billion as opposed to billion, right? Okay. So in the real world applications, most often the adjacency list representation is preferable for that reason. Does that make sense to everyone? Any comments people have, maybe? Objections? Always good to bring up objections.
Yeah, so just
Yeah.
double checking, you mean
Yeah.
that the adjacency matrix wastes space because you have to list every edge twice?
It wastes space if the graph is dense, right? If I have way too many edges, right? Adjacency matrix representation. Well, for an adjacency matrix, you need billion squared entries anyway, right? Because you can't avoid it. You have a matrix which is billion by billion, in this case 13 by 13, and you need that many bits, billion squared bits. In the adjacency list representation, you would waste space if your graph is what's called dense, has too many edges. As you've just remarked, well, maybe it wasn't you, but who just remarked that it would be close to n squared? Can you explain to us one more time? David, is that you?
Yeah, that was me. If you have every node in the graph being connected to every other node, then all billion nodes would have a list 1 billion cells long. So it would be equivalent to a billion times a billion.
Yes, exactly. Does that make sense to everyone, right? Okay. So, but usually you don't get dense graphs in the real world. So adjacency list representation is preferable for that reason. Make sense? Here's the adjacency list representation. Okay, so what we'll use, it says a bag here, but we didn't cover bags. It's a very simple data structure. So we're using, in our graphs, we're using array lists, simple array lists to represent these adjacency lists, as you'll see in the code. So if you go here, we're using array lists, Java's array lists to represent this adjacency list, right? Which is also simple, but it can be even simpler using what's called a bag. A bag is simply a collection of items. You just throw in items in the bag, and all you do with them is iterate through them. You don't have any fancy operations on these items in this collection, the bag collection, like we have on the array lists, like inserting stuff in the middle and all of that. A bag is simply a collection of objects. You throw those objects into that collection called a bag, and all you ever need from a bag is just to iterate through the collection. And for the graphs, that's all we need. But we're not bothering with further simplifying this by using bags, because we can, I think array lists are clear to every one of us here, and we'll just call them array lists here. That's fine. But just to remark that it can be even simpler. Okay, what else do we? Okay, so here's an example of a dense graph on 1,000 edges, like too many edges. All pairs are connected, close to what's called a complete graph. A complete graph is a graph in which every pair of vertices is connected by an edge. Here's a sparse graph on 200 edges, with 200 edges. And both of these graphs have degree 50. The number of vertices is 50 in both of these graphs. Very different graphs. Okay. Okay. So an adjacency matrix takes that much space. Adjacency lists take that much space. Okay. This is just a simple table summary of the space taken by these two different representations. Okay. Okay. All right. So maybe we'll return to this later. Okay. So here's an adjacency list representation. So we've already seen this. This is you have this code. It's here. What you see here is exactly what you have in this constructor here on the left. So when you're done, by the time this constructor is done, you've built a graph with the empty array lists. Okay. And then you can add these edges here as you wish. Okay. And because our adjacency list is an iterable object already, because it's an array list, so we just simply return this adjacency list. Oops, adjacency list there. Okay, so I think people get an idea what's happening with this. Okay, so this is a very compact and nice representation of a graph, right? Okay, so it says this is what we're planning, but I think people have already downloaded, experimented with the graph, with the graphs that you have on Canvas. So if you haven't, please do this. Okay, these are all nice exercises here with what we're planning to do, but I want to do something else also today. I want to do a sample problem for quiz for the upcoming quiz. So we'll skip this piece. We do want to cover depth first search. So what is depth first search? Here's a sample graph. Some of you, if you're a gamer, you may recognize this this graph is from Pac-Man. It's a Pac-Man game. So edges represent passages. Vertices represent the intersections of passages. So here, for example, is a vertex. Okay. Okay. So if you want to explore a maze like this, there is an ancient algorithm for doing this. Okay. So when Theseus was sent to slaughter the Minotaur, Ariadne, some people pronounce this as Ariadne, which is probably in English is the pronunciation, gave him a ball with a string, right? So he wants to get into, and do we have this slide coming up? Yeah. Okay, so here's the Minotaur, okay? And this is Theseus here, wants to slay this Minotaur. And he was given this ball with a string like this. So this is the ball. He stretches the string so that it doesn't get lost in this labyrinth. Okay, so he comes here, for example. Okay, then he marks exactly where he is. He's right here. He continues stretching the string. So now at this point, when he's in this position, he has several ways to go. Okay, so it picks one at random. Let's say he picks this way to go. This is shown in the third panel here. He comes down here, stretches the string again. Now he has only one option. Okay, so he goes up this way and notices that he has already been there. So he unwinds this string, comes back, then he comes back again and explores a new direction. This is called depth first search. So he started here and explored it to the very depth until he couldn't go no more. So 1, 2, 3, 4, and he unwinds back, comes back to where he has another option to explore, and then goes all the way down to explore this other option. So it comes down here, here, and then now it sees that it's explored, so it comes back, and then sees so finally gets to the destination. This is the idea of depth first search, right? Okay, so it's surprisingly simple to implement. It's a very compact, once we have this graph representation, it's very, very compact code. Okay, so we should mention that Claude Shannon experimented with mice to determine whether mice actually have a sense of the depth of, can understand the depth first search algorithm, and apparently they did. There is some indication that they can search mazes using depth first search, which is interesting in itself. Now, if you go to Canvas and download this maze exploration, you also have, you'll have this maze. If you simply run that, you can run this, okay? So if you run this maze, you'll get, this is what I got here. Okay, let me run it one more time. So if you run this maze, okay, so this is what it looks like. So notice that it's running. So this time it found it pretty fast, got to the destination. So it was exploring the depth first search. This is exactly the Fermat's algorithm that we just talked about, right? So notice now this one is, so each time you get a different run. So sometimes it can get pretty frustrating because you can see that you're approaching the target, but it backtracks. Okay, this one was not such a bad run, but anyway, you get the idea. You can take a look at the way this is implemented and see how it works. Okay, now back to where we were. Okay, first of all, okay, this is where we were. You guys see my screen still? The slides?
Yeah.
Okay, so now I don't want to do this. Okay, you can have larger mazes. You can experiment with that code that you already have, and you can increase the size of the maze if you'd like. Here's the depth first search. It's remarkably simple. All you have to do, I'm going to run now a demo of depth first search. But the code itself is remarkably simple. Okay. Okay, we don't need presenter notes here. Just get some real estate on the screen. All you have to do to systematically traverse this graph in a depth first manner is simply mark each vertex. So you start at a vertex, the depth first search algorithm starts at a given vertex. And I don't know how many people are listening to this right now, probably like 5 out of 40. Okay, so you start at this vertex, V, and then you simply visit, visit the neighboring vertex and mark it, and keep marking it. So let me actually, it's easier for me to do the demo. You see pseudocode there, that's all there is. What you see on the screen is all there is to it. Demo, which demo should I do? I have a bunch of demos. Depth first search, directed, so let's stick with undirected. Let's do this one. Okay, so let's see how that works. No, this is breadth first search, sorry. We need depth first search. How about this one? So here's how it goes. Here's our graph. It's still going to be our tiny g graph. Okay, so you have 13 vertices, 13 edges, and the entire algorithm is those 3 lines that you see at the top here. This is okay. So let's see how that works. We're going to keep 2 arrays. One we'll call marked, and the other edge 2. You'll see the purpose of edge 2 in a second. We want to keep track of the vertex from which we came to this marked vertex from. Let's see how this goes. So that we can, what we want to do later is to recover the path from some vertex back to the original vertex from which the depth first search started. So let's take a look. Okay, you start from 0. You visit it. Mark the vertex as visited, first line. So here it is. You see it's marked as visited here. So you mark it as true. So this marked array is going to be a true false array, initialized with false as first. You visit the vertex, you mark it as visited. Well, how do you do in Java? You set this value to true. So you mark it as visited, true. Okay. Then you look at its neighbors. So you have inside the graph is already represented inside your computer. You have an adjacency list of that vertex, which you've just marked, right? This is according to the graph API that we just discussed. So you look at its adjacency list. The order in which you visit them doesn't matter. The adjacency list itself for any given vertex is built depending on how graph was stored initially in the text file that you read. But anyway, suppose you read 6 first. 6 is the first guy on the adjacency list. So you visit 6, you mark it. You put T here for 6, and you also mark the edge from which you came to T. We'll see how useful that will become in a second. So you say that you came to 6 from 0. This is called the edge 2 array. Okay. Okay. Then you look at 6 adjacency lists. 6 adjacency list. Well, 0 is on it, but 0 is already marked. So you recursively visit all unmarked vertices. Now 0 is already marked. So you continue looking at what else is on 6 adjacency list. And the next, so you do nothing here at this step of the algorithm. So there's also 4 there. Okay, so now 4 is not marked. So what do we do next? Help me out. So what's going to be on the slide coming up next? What do we expect?
4 gets turned to true in your marked array list, or your marked array.
Yes, exactly. So that turns true, and I also mark where I came from. So the circled entries are the ones that we change. Okay. Then I looked at 4's adjacency list. Well, I have 6, but 6 is already marked. So I looked, apparently 5 was the first one on that list, and 4's list. So I look at 5. 5, again, I update 5. Then look at 5's adjacency list. 3 is on it. Mark 3. Then I look what's on 3's adjacency list. Well, there's 5, but that's already marked, so you forget about it, do nothing. 4 is already marked, so you do nothing. And now, this is the first interesting place, and there's nowhere else to go from 3. So you backtrack now. So now you come back to 5. Now this is unwinding that string in the labyrinth that we saw. This is unwinding his string, going back to the corner from which you came, 5. Okay. Now you can go, where can you go from 5? There's this edge to 0 that we haven't explored, but 0 is marked. So 4 is marked. Okay, so 4 and 0 on the adjacency list of 5, but both have been marked. So now there's nowhere else to go from 5. So you return. So you guys are paying attention, right? How this is updated. This is the memory. It's the memory inside me. Okay. So 4, what's happening with 4? You visit 4, 6, already marked. There's nowhere else to go. well, you still have to explore. That's marked 2. So 4 is done now. Okay. So you backtrack to 6. From 6, where else can you go? Well, you have 0. That's already marked. There's nowhere else. So when you visit 0, that's good. Now we're all the way back up. Now we're back up to 0. So remember, 0 was on the adjacency list of 0. I had a bunch of vertices. I had 6, 2, 1, and 5. Well, because I started from 6, I went all the way like depth down. So I went to 6, and then anywhere I could get from 6, and this is called depth first search. So you get the idea. Now, when I backtrack to 0, then I have other vertices on its adjacency list that I haven't yet explored, unmarked vertices. So I look at those. In this case, 2. Well, there's nowhere from 2 to go, but to a marked vertex, the 0 vertex. So I'm done with 2. You update these arrays here accordingly. So note what's happening with the arrays. And then, okay, so now I do it with 1. 1, nowhere else to go. Backtrack to 0. Now I'm done. Notice what's happening also here. Now there's nowhere else to go from 0. This component here, and this is kind of looking ahead a little bit, but it's worth discussing now. It's called a connected component of the entire graph. In this graph, I have 3 connected components. Imagine I could have like another counter here. This one doesn't have it, just as this is a simple depth first search. Another counter that would count the number of connected components in this graph. So right now, when I'm done with this connected components, and I'm done with this connected component because there's nowhere to go from 0, I would increment some counter that counts in the entire graph the number of its connected components. So I would register it somehow inside my program that I'm done with one connected component. Why? Because I've explored everything from 0, and there is nowhere to go. I have some marked vertices here, and some vertices are unmarked, which means that I haven't yet explored them, and I have no way of getting to them, to those vertices, as things stand now. Okay, but then because I have a bunch of unmarked vertices, I pick the next unmarked vertex that I can find. Let's say it's either 7 or 9, doesn't matter. So I continue. I pick up the algorithm continues. I mean, that was what I've just remarked about connected components, was kind of a side issue here for us for now. Okay, let's continue with this demo. So now the next one. Okay, so first of all, this depth first search actually from 0 is done. This algorithm is complete because there is no way of reaching the other connected components here. All right, so 7 and 8 will never be reached. But notice, because we had this edge to array, what we're also able to recover by looking at these entries and reading backward, the paths from, although this is a tree actually, the path from any vertex back to the source root being 0. The vertex from which we started this depth first search. So for example, take vertex 5. Where's 5? Here it is. The edge to entry for 5 is 4, telling me that I came there from 4. You did something similar with a tree exercise earlier, so they should make complete sense. So you came from 4. So here it came from 4. So that's 4. Then I look at the entry for 4. Where did I get there from? From 6. So 4 from 6. Then I look at the entry. Then I look at the entry for 6. How did I get there? Well, it says I got there from 0. So here's the entry in 6. I have a 0. So I've recovered the complete path from 5 up to 0. Right? So just iterating through this until you reach this dash here. Okay, you can imagine having a little for loop that recovers the path, prints the path. This would be a good programming exercise for you to run this and print the path. How do you run this? Well, the code is given in the slides. Okay, so let's continue where we left off. Continue this. This is our DFS code. Okay, and there are typical applications, and okay, so we'll talk about how to implement the applications later. But for now, so one application is clearly maze exploration. I think it would be enough for now. Just consider maze exploration. Now, the thing is, how do you design this depth first search? Okay, and I think we've already shown this, but it's worth repeating. The design pattern that we have is that we decouple, this is kind of important, that we decouple this graph data type that we showed a minute ago in our IDE from the graph that processes it. So what we'll have is we'll create a graph object, and then we'll have a separate file. So the way you do this whole homework assignment, you'll have a separate file that will do the graph processing itself. So first, you create a graph object and pass the graph to the graph processing code, which is lives somewhere else. So this makes complete sense from software design perspective. Now you see, you go on the internet and a bunch of libraries exist. People have these graph processing libraries where they place all that graph processing code inside the graph data type. That is not a good way to do this. This is something called the FAT implementation of a data type. And it's a good idea for many reasons. And we don't have the time to discuss those reasons here, but in a software engineering course, you will discuss those reasons. There are many great reasons to keep your implementations very lean, okay? Just keep the stuff that you need and not that much more. Okay. So you separate this, decouple the graph data type from the processing. You have separate, you create a graph separately, then you pass that graph to a graph processing routine, and you query the graph processing routine for all the information that you need, like the paths. What is the path from that vertex 5 to the start, and so on and so forth. That's the way we'll do it. Okay, so you can imagine this other class here called paths that finds the paths from the source S in the graph. Okay, so I'll let you take a look at these. So let's see what else we have. Okay, so what were the, okay, so this was our depth first search algorithm. So what were the data structures here that we used? The simplest one, actually, the simplest ones, right? So we had one array. We just had a couple of arrays. That's all we had in terms of data structures to just run this algorithm. Turns out it's very simple. But, okay, this marked array, the Boolean array, and then the other, we have this integer array. Why integer? Because we marked our vertices as integers. Okay, this is just simplify code. Okay, and this H2 keeps track of the paths. That's all the rest of it. There are all these recursive calls. Actually, implicitly, this is a stack. That's there in the background as well. But this is, the stacks show up in the recursive calls themselves, right? So you recursively mark all these unmarked vertices that are adjacent to V, right? So that's a stack of calls, function calls. Here's the entire depth first search implementation. It's not, okay, it's not super complicated. So again, this is a separate class. Okay, notice that its constructor here receives a graph. Okay, there's some initialization code that you can figure out what it is for the homework assignment. But the whole depth first search itself, that's all the rest of it. That's entire code. Okay, that's where you figure out how to. So you start. So the DFS. This is the DFS, the method. Inside this is the graph processing code, so decoupled from the graph implementation. Okay, it receives a graph and the start vertex. And then once it receives the graph and the start vertex and understands what the graph is and where the start vertex is, just simply calls the depth first search with this graph, passes this graph and the start vertex there. And that's it. And then you can, from this, you can do this, you can add a couple of smaller methods like, I don't know, print the path from here to here. That would be a good exercise. Maybe we'll get to do it one of these classes. But okay, now we're going to skip the properties of this for now. We're going to skip the proofs. We'll discuss them later. Now we want to get to depth first search. Okay, there are a couple of applications. So for example, here's Taj Mahal, right? So somebody took this picture and didn't like the color of the sky here. And to improve the color of the sky, you bring it into your Photoshop, right? And what does Photoshop do? It runs depth first search. How does it run the depth first search? It actually, this picture itself is a graph of millions and millions of vertices. The vertices whose colors are similar are connected. They're the blues are one connected component. The blue connected component, so vertices whose color is blue are in one connected component. Those are vertices that are white, for example, or gray, or red, or reddish. They're in a different connected component. Okay, so when you do this, like the magic wand thing that's in there in Photoshop does exactly this, breadth first search. You start from a pixel and click on that magic wand. It does the breadth first search and looks at all the connected, finds the connected component with this blue vert in which this blue vertex is, and recolors them. So notice the difference. This picture on the right the sky looks much better, right? Okay, so you get the idea. There are plenty of applications. There are other applications. So here's another application. I'll let you read that on your own. So we don't have time for that. Now, breadth first search is the next thing. Before I get to discuss this, I want to do something else. Here's what I want to do. I want to switch. I want to do a sample example that came up on one of the previous exams. So I want to do that one to make sure you're well prepared for the quiz and that there are no questions, there's nothing unexpected, none of that stuff. First of all, do people remember what hash functions were, right? People have done this reading assignment. What's linear probing? Can someone remind me while I'm looking? So this was one of your reading assignments from before. And while I'm looking for my sample problem, can someone remind me what linear probing is?
So sometimes after you hash a bunch of objects, two will end up with the same hash code and they will conflict with each other. In that sense, and linear probing is a way to find the item you're actually looking for when the hash codes are the same.
Yes, that's exactly right. Now, if I can only find, all right, how about this problem? Okay, so can someone help me solve this problem, please? This one showed up, showed up in one of the quizzes. Please read it. Imagine you're on a quiz, and would like to solve it. See what's happening. Let me see if I can copy this entire thing. Somewhere. And scratch paper. This looks a little better. This is what I wanted to have prepared for you so that we didn't lose all that time, but nevertheless, here we are. Now we're in business. All right, so what is it that we're asked to do here, please?
First, you use that modulus operator. So like, for example, that 14 mod 13, going to, that's your hashing rule. So basically what you're going to do is, say again?
What was 14? I'm sorry.
Sorry, 42 mod 13.
Okay, let's start with 7 in this order itself.
Oh, sure, yeah. So you would do 7 mod 13.
Okay, 7 mod 13.
And you would just get 7. And so you would index, under the 7 index, you would index 7.
Okay, that's right. Then I would look, okay, so what's the next step? That's great. That's exactly right. So let's see, let's just do this one
for every step. And if there's any collisions, then you resolve the collision using the linear probe.
Okay. All right. So let's just go through this example. I think it's great that this example is super clear to some people at least, but let's make sure it's clear to everyone because you'll see this example. So you do this 42 mod 13. So 42 mod 13, well, it leaves 3, right, as a remainder. You divide 42 by 13, you're up in 39? That's 3 times 13. 3 times 13 plus 3 is 42. So my 3 is the remainder. So that's going to be 3. So apparently 42 goes into the slot 3. So here's my 42. That's where it will go. You may be asked to fill in this hash table, just like that. This is the hash table. It's also asking, the hash table is this piece, of course. This is asking you to actually count the number of collisions, how many times. Okay, when you put, okay, so I should be accounting for this now, maybe. It's kind of, should have said that. When you put a 7 there, you're essentially doing what? How many collisions did I have? Well, I had no collisions. I didn't collide with anything. So here I have no collisions. This key collided with nothing. When I put 42 there, collided with nothing. Okay, so I have no collisions there. Okay, then I look, so I've just processed 7 and 42. Now 30 mod 13, that should be 4, because when you divide 30 by 13, you get 26, twice 13, and then 4 is the remainder. So apparently 30 goes in here. Did it collide with anything? No. So these new elements are going in there like nicely. No collisions. Okay, so notice how, by the way, when I want to retrieve an element, what do? I want to get this key. This is a way to implement the set, if you remember. Okay, I could also have an association of a value with a key. So I'll be storing those keys inside those indices, but at those indices. And then with the keys, I can also have these values associated. Okay, but that's fine. Let's just keep the keys only for now. So you store the key. The key is that goes into 30, no collisions. Everything's nice. Now, okay, so when I want to retrieve 30 from the list, what's the computation that's being done before we continue, please? Okay, so the whole idea of this hash table is that I get to retrieve my keys super duper quickly. Okay? Unlike those other structures, the the lists or whatever that we considered, where you had to traverse the list, the advantage of a hash table was that I can, retrieve the stored keys from the hash table very, very quickly, almost in linear time, almost in constant time, right? So suppose I wanted to get 42 out of the array. What do I do, please?
You would perform the hashing function on 42 and then navigate to that index.
Yeah, exactly. So it's pretty quick, right? The computing this hash function 42 mod 13 is super duper quick for a computer. It does it in constant time. So it computes that index. So now you have an index. So now you're looking for 43, it's stored at index 3. So you go right into index 3 and retrieve that 42. That's just how it works. Okay, so let's continue with this example. So we've inserted 3 elements. Now I want to insert 16 into this. So 16, I compute 16 mod 13. So apparently 13 fits there once, but then leaves a remainder of 4. Okay, so what happens here then? 16, oh, I'm sorry, 3. What did I just say? Did I say that was 4? Should I have said that it is 3? Is that right? So leaves a remainder of 3. So 13 fits into 16 once and leaves a remainder of 3. So therefore, 16 would go into 3. Here's the 16 wants to go there. But this 3 at index 3, that slot is occupied by 42. Okay, so it collides with 42, goes, so what's the next step from the reading assignment, please? One of you just said it. Ben, was that you?
Yeah, I honestly don't remember how it's implemented, but we have to do the linear probe.
Yeah, that's all we need for this one, by the way, right? This will show up on the quiz, but I don't know if you'll be asked about the implementation. We'll do another example later. For now, like this was, there's no explicit question about its implementation. Okay, so 16 goes here. Then, so it collided with 42. That's one collision. Then it checks the next one over. Can I go into the 4th slot then? Because the 3rd slot was occupied. So it's 4. No, that one's occupied too. 30 is sitting there enjoying himself. So that's another collision. So then 16 tries the next one, 5. Oops, that one's open. So that's the slot it can go to. So it goes into slot 5. That's where 16 goes. So let's write that. 16 goes here. But then I mark that I had 2 collisions there to get to 16. I had experienced 2 collisions to get to 16. So I mark it in the number of collisions. It took me to insert 16 into this hash table. Okay, then 1 comes along. 1 hashes where? Is just 1. So 1 goes there without any problems. Then comes 2. 2, also no problems. Mod 13, that's just 2. So that's not occupied, empty slot, goes there. Now comes 28. So 28, mod 13, that's, I think, 2 again, because it's twice 13 plus 2 is 28. So 2 is the remainder. Therefore, 28 goes right into this slot here. So here's 28 wants to go in here. So this one is occupied. Okay. Then it checks this one. That's the second. That one's occupied. Then it wants to go into the next one then. That one's occupied. Then this one wants to go there. That one's occupied. Until it finally finds a slot 6. That's not occupied. So it goes into 6. 28 goes into 6. And what should I put under the collisions, please?
4.
Yeah, 4 is the number that it took there. The number of collisions it took for me to insert 28 into this hash table. Does that make sense? So just wanted to do this example to make sure that people are aware of what's happening here, because you'll see this one on the final, if not on the quiz, but likely on the quiz as well.